For example, here's a histogram. Let me just close this other window. Here's a histogram. Let me blow it up a little bit. Okay, here's a histogram that displays the heights of a sample of black cherry trees. And on the vertical axis, we have the frequency, the number of trees in the sample that fell within that category, 60 to 65 inches, 65 to 70, 70 to 75, 75 to 80, and so on and so forth. So one of the things we might ask you here is to tell us, well, for instance, what's the probability if we randomly select a black cherry tree, what's the probability that it's over 80 inches in height? Well, to determine that probability, we know we take the number of cherry trees that actually exceed that satisfy our criteria, which is going to be 5 for this bar and 2 for this bar, 7 over the total number of cherry trees. Total number of cherry trees is going to be 3, 6, 14, 24, 29, and 2 is 31. So it would be our 7 over, did I say 31? 7 over 31. If I asked you to find the median height for cherry trees, well, where would that be likely to be? Well, we know the median is going to be the middle value. Since there's 31 cherry trees that are in this sample, the median value is going to be the 16th. Is going to be 16th cherry tree, the middle value, middle height. So we can count either up from the bottom or down from the top to find which bar the 16th cherry tree is. First 3 are in here, second 3 up to 6 are in here, up to number 14 is in this bar, and the 16th cherry tree is in the bar represented by the height 75 to 80 inches. So the median is between 75 and 80 inches. Okay, if I asked you about percentiles, well then instead of looking for the 16th cherry tree, I'd be looking for probably the 7th cherry tree, the middle of the lower median, the 25th percentile, and 75th percentile, I'd be looking for the middle or 7th or 8th cherry tree from the top for the 25th and the 75th percentile. Hopefully, if we gave you one of these numbers, it'll work out a little bit more evenly than this. But I think you've gotten a look at that already on the homework problem. And that's some students really still get kind of crossed up on this, but that's basically what we're looking for. If you, a lot of these different histograms can take various shapes. They could be very spread out, but try not to be thrown by something that looks just a little bit different than this. The principles are basically the same for all of these. So try to just use your judgment about it and not be upset by something that looks just a little bit different than what you've seen in general. Because we might like throw a little bit of curve at you and give you something that's just a little bit different shape than you see there. But the median is going to be still the middle value, and the 25th percentile is going to be the 25th at the point where 25% of the values are below that and 75% above that, and the quartile range between the 25th and 75th percentile, and so on and so forth. The only other thing that I might be concerned about there is that, for instance, if we asked you, let me show you another one. Here's another one. This one has to do with the heights of people. If I told you that the average, the average height, let's see, I don't like that one. No, I guess we can use this one. Okay, this is the 160s, 170s, 180s, 190s, and so on and so forth. This is the heights of 30 people. This the most frequent, the mode or most frequent outcome is in this bar over here. The median we could figure out again because this 30 people is going to be basically the 15th or 16th person. And I can already see that the 15th or 16th person is going to be in this same bar where the mode was the tallest bar here, and so on. If I asked you, for instance, that given that a person's height is greater than 160, what's the probability that their height is also greater than 180? Well, 160 is everything from here to the right. 180 is everything from here to the right. So there are 7, 5, that's 12, 14, 15 people whose heights are greater than 160. And out of those 16 people, 2 and 1, 3 of them have heights greater than 180. Okay, so it's 3 over, did I say 16? 3 over 16? That's a conditional probability, right? Because given that the person's height is over 160 centimeters, what's the probability that they're over 180 centimeters? Right, so that's another way that you might take a look at a conditional probability. So you might get a few questions that look something like this. Okay, let's go back to this. You guys okay with that? Feel comfortable with that stuff? I mean, we kind of pounded the life out of those histograms, I think. Let's take a look at diagnostic tests. I threw up 2 forms of what this question might look like. Diagnostic test 1, diagnostic test 2. I'm going to start with number 2 because it's a little bit clearer. And I'm going to pull up Excel because I like using Excel to do calculations because it's really convenient. I'm a little bit hoarse because I was at the Jet game and I was screaming a lot. I lost part of my voice here. They still lost anyway. It didn't help. Let's see. Okay. Okay, so I'm going to put these numbers in here. 48. Actually, yeah, 48, 2, 95, and 855. Okay, and while I'm at it, I'm just going to highlight this and put this box in here. The selections don't show up that I want this. I make it a little bit wider. There we go. Put these borders in there. Okay. Now I notice that this is disease positive, right? This is disease negative. This is a positive test. This is a negative diagnostic test. Okay, and we see that there are 50 people in this sample that have the disease. There are 950 people that don't have the disease. And there's 1,000 people altogether in this study. Okay, now let's see what we were asked about here. What's the sensitivity of this test? Well, the sensitivity of the test is the probability that you correctly identify someone that has the disease and that they test positive. So the probability that someone tests that has a disease, that they're correctly identified and they test positive, is going to be 48 out of 50. In other words, the probability of a positive test, given that they have the disease, that's equal to, oops, let me close that parenthesis. That's equal to 48 over 50. Oops. Enter. Here we go. The sensitivity of this test, that's the sensitivity. Okay, and I put this in here just to get us used to that kind of notation. Okay, next question on there is, what's the specificity of this test? Specificity of this test is how good we are at identifying people that don't have the disease. And it turns out that specificity, right, the probability that they test negative, given that they're disease negative, right? Percentage that were correct. Well, that's going to be equal to, let's see, out of 950 people that don't have the disease, we correctly tested, got a negative test for 855. So that's 855 over 950. Oops. Dang. That's 90%. The sensitivity of this test is 96%. Specificity of this test is 90%. Okay, so now usually we like to express these probabilities or specificity as decimal fractions between 0 and 1. Okay, so what's next? What's the positive predictive value for this test? Well, let's take a look at this. How many people actually test positive in this test? That's that row over there. Well, the number of people that actually test positive is the sum of not 48 and 95. 143 people actually test positive. While we're at it, how many people tested negative? Equal to the sum of 2 and 855. I guess I could have written that down. Right, and that does add up to 1,000, so it kind of checks our work a little bit there. Okay, what's the positive predictive value of this test? Well, in this sample from this population, we found that we got 143 positive tests. Out of that 143 positive tests, 48 of those people had the disease. So what are we looking at here? Positive predictive value. That's what's the probability that you have the disease given that you've tested positive, right? A conditional probability. Given that you've tested positive, what's the probability you have the disease? So that's going to be equal to the number of people that have the disease and test positive, which is 48, out of the total number of people that tested positive, whether they had the disease or not, which is 143, right? Aren't these always the number of people that satisfy our criteria over the possible number of outcomes, right? Whether it's a conditional probability or any other kind of probability. Okay, so that's about 34%. Positive predictive value is about 34%. We haven't talked about it too much in class, but we can also calculate the negative predictive value. So if you have a positive test, if you go to a doctor, take this diagnostic test, you have a positive test, 34% of the time you will not you will have the disease. The other 66% of the time turns out that the test was wrong and you don't have the disease, right? A little bit of a distressing situation, but that's what happens with these tests sometimes. Probability, let's see, negative predictive values and probability that you don't have the disease given that you've tested negative. Okay, and what's that going to be? That's going to be equal to, well, 857 is total number of negative tests. The number of people that don't have the disease that actually correctly tested negative is 855. So this is 855 divided by 857. So that's almost 99.8% of the time. If you test negative, you don't have the disease. Okay, so that's a pretty good outcome there, right? So let me see, specificity, okay, good. I think we're okay. All right, so let's move on to, I think we asked one more thing there. What's the prevalence of the disease? Assuming that this is a random sample from the population, these 1,000 people, what's the prevalence of disease? Anybody want to tell me what the prevalence is? I'll leave that up to you. Probability of having the disease in the population. Anybody know what that is? Somebody tell me what the prevalence is, so I know you guys are awake and you can hear me. Good work. Up. Hang on a second there. Hang on a second. I spoke a little too soon, Leonardo. Good work, but we're off by a little bit, right? Prevalence is the number of people in the population that have the disease over the total population, right? The percentage of people that have the population. That 48 is the number of people in this sample that have the disease, but that's only the ones that tested positive. You still have 2 that tested negative, but they have the disease too. Just because the test didn't detect it doesn't mean that they have the disease. So yeah, the correct answer we want is 50 over 1,000, which is the prevalence. You don't have to be. Yeah, I've had a long day too. Yeah, is equal to 50 over 1,000. Okay, or about 5% of the population has this disease. Now, one of the things that you may come across as we work on this a bit more, as you get into more involved problems, is that you're going to notice that as the prevalence goes down, as you get diseases that have a lower prevalence, the positive predictive value becomes lower. Okay, you're going to have more. That you have more people that don't have the disease that are being tested that wind up as false positives that wind up pushing this number up without increasing the number of people that are correctly diagnosed. So as the prevalence goes down, the positive predictive value of the test also goes down. Okay, we demonstrated that, I think, in the homework, and I think if you go back over the Thursday session that I posted, that's on YouTube now that I posted, you'll get a look at that from the example that we worked out for the homework. Okay, great. Another way for us to maybe approach this problem would be something like this word problem. Suppose there was a diagnostic test for diabetes that was 90% accurate on individuals with diabetes. Okay, 90% accurate with 90% accurate on individuals with diabetes. That's the specificity, isn't it? If it's 90% accurate for those with, if it's 90% and it's 90% accurate for those without diabetes. Okay, in other words, that's how good it is at giving a negative test for people that don't have diabetes. That's the specificity. So 90% sensitivity and a 90% specificity for this test. Okay, produces a negative result for 90% of healthy individuals. In other words, they don't have diabetes. This test was applied to a population where the prevalence is 5%. Well, that looks a lot like the sample we just looked at, except that the specificity and sensitivity in this test was a bit different than what this is, right? So what are the questions we're going to get asked on this? If an individual receives a positive test, what's the probability that that patient has diabetes? What is that? If an individual receives a positive test, what is the probability that they have diabetes? What's the probability, given that they tested positive, what's the probability to have the disease? Probability of D plus bar D over D plus bar T positive, right? That's the positive predictive value. Okay, let's not jump to conclusions yet. Let's actually calculate it. And I'm actually there's a couple of ways that we can look at to do this. One way, I'm going to pull up my writing board here. I can find my notepad. And one way that I might look at doing this is I might draw my own little table here, right? The prevalence is 5%. So I'm going to create a sample. Okay, let me try and get this as straight as I can so I can work on it pretty good. Okay, this is disease positive, disease negative, test positive, test negative. And I'm going to say I'm going to work with a population of 1,000. Okay, maybe I'll call it 100. What the hell? Okay, I'm going to call it a population of 100. 5%, the prevalence, probability of having the disease is equal to 0.05. It's 5%. So out of 100 people, we would expect, I'm going to make this 1,000 instead so I stay with whole numbers. 5% of those people actually have the disease. 5% of that is 50 people, right? That means 950 people don't have the disease. See, this is a construct. I mean, if we took a sample and turned out from this population, and if the sample turned out perfect, this is what it would look like. I'm building this artificial sample so that I can test these various values. Okay, so now we said the sensitivity of our test was 90%, and the specificity of our test was 90%. So if the sensitivity is 90%, 90% of the time we're going to correctly get a positive test for these 50 people. Well, 90% of 50 is 45 people. So we're going to get a negative test for 5 of those people. 10% of the time, in other words. Okay, so what about people that don't have the disease? It's 95%. Well, our specificity is 90%. So 950, right, times 90% of the time we'll get it right. We'll go in here. I'm going to do 10%, and 10% is 95, right? So the remainder has to be in here, and that's 855, right? That adds up to 950, I think. No, I'm wrong. It doesn't. 845. No, 855. Yes, 855. Yeah, it adds up to 950. So the number of people in this population that get a positive test is going to be 140. Number of people that get a negative test in this population is going to be 860. Okay, you guys can check my math for me. Now, what's the probability, the positive, in other words, what is the, if an individual receives a positive test, what's the probability that the patient has diabetes? In other words, given that the patient has tested positive, given, what's the probability that the patient has diabetes given that they've tested positive, right? Isn't that what that says? Individuals use a positive test. In other words, given that they've tested positive, what's the probability I have the disease? So given that they've tested positive, what's the probability I have the disease? That's the same thing as the positive predictive value. And again, given that they've tested positive, well, 140 people have tested positive. Out of that, only 45 have the disease. So the positive predictive value is 45 over 140. And you can turn that into a decimal for me. Okay, so that's one way for us to solve this particular problem. Okay, another way for us, I'm going to come to another way to solve this particular problem. First, I'm going to take a look at the second part of this. The second part of this says, if an individual receives a negative test, what's the probability that the tested patient has diabetes? Okay, if they get a negative test, what's the probability that the tested patient has diabetes? Well, if we were looking at the negative predictive value, we would be looking at probability that if the person tested negative, that they don't have the disease, right? That's the negative predictive value. That's not what they asked here, is it? They asked here is if an individual receives a negative test, what's the probability that they have diabetes? Whoa, that's a little weird, right? Normally we'd ask for that. That's kind of a curveball. Maybe we won't see that kind of a curveball here. That's usually what we'd see. Usually what we'd see is this, right? Maybe we won't see this curveball where what they're asking, what's the probability you have the disease given that they've tested negative? But how would we solve that? Let's take a look at that. What people have tested negative? Well, 860 people have tested negative. What's the probability they have the disease given that they've tested negative? Well, only 5 people out of those 860 have tested positive that don't have only 5 people have the disease among all of those that tested negative, right? So whatever that fraction comes out to. Yes, Simon, thank you very much. Okay, so that's kind of this bottom one's kind of a curveball because normally they wouldn't ask you. That's kind of like interpreting your understanding of it, I guess. More likely, you would be asked to just find a real negative predictive value. That would probably be a more common outcome. Now, there's another way for us to solve the specificity, and the prevalence. You can calculate the positive predictive value without having to build that table. Okay, let's do it for one of the examples that we just did, like right now. Okay, so if we do it for this example, let's see. What did we say that the prevalence was here? It was 0.05, right? So I'm gonna fill this in. I'm gonna first move this out of the way a little bit so I can see it a little bit better. Oops. Okay, let me move this. I can use this little corner over here. Okay, So let's see, the sensitivity here was, what we say our sensitivity was? It was 90%, right? We could actually, if we had the table, if we work on the table, we could calculate that 45 over 50 is going to be 90%. The specificity is 90%, and the prevalence is 0.05, 5%, right? Remember, we decided that we're going to work with something. Prevalence was 5%, 50 over 1,000. Okay, so let's work out this formula. So the positive predictive value is equal to the sensitivity times the prevalence, which is 0.9 times 0.05, divided by, sing with me, sensitivity times the prevalence. Oh, you know, I'm confusing this. How come you people are not helping me here? Okay, this is the sensitivity times, not 1 minus the prevalence. I keep looking back and looking at the wrong formula. The sensitivity of positive predictive value is equal to the sensitivity times the prevalence, 0.90 times 0.05, which comes out to 0.045, okay, divided by the sensitivity times the prevalence is the same as that, which is also 0.045, 0.045, plus 1 minus the specificity, which is 90%, 1 minus 90% is 10%, times 1 minus the prevalence, okay, which is going to be 0.95, 0.95, which is going to be 0.1 is going to be 0.095. So this is 0.0545 plus 0.1 times 0.95. The prevalence is 5%. 1 minus the prevalence is 0.95. A tenth of that would be 0.095. This is going to be 0.045 divided by the sum of these two, which is going to be, let's see, it's going to be 0.140. I'm going to move something over here. Remember when we calculated the prevalence? That look familiar over here? We got basically the same ratio over here. It's the same answer. This answer and that answer are the same fraction. So as long as you keep your terms correct, probably the best thing for me to have done is to hide this formula for the negative predictive value, so I didn't keep looking over and look at the wrong one. But are you guys okay with that? You can actually use that formula to work out what the negative predictive value are. Oh, yeah, excuse me, Bashinda. You noticed that I kept looking back and looking at the wrong, right? I started looking at one formula, I'd look away, go back and look at the wrong formula. So I was mixing the two of them up, right? So you guys understand as long as you guys understand why I was struggling with that, because I was glancing, I actually really should have hid the second formula so I didn't confuse the two of them. But yeah, that's the one that we were using for negative predictive value. Now I just want to show you, let's interpret this formula. So the sensitivity times the prevalence. Well, the prevalence is the percentage of people in the population that have the condition, right? And the sensitivity is the percentage of people that you'll correctly identify with a positive test. So the top here is all of the people that both have the condition and test positive. That's what's on the top here. Those are people that have the disease and tested positive, where our test worked. On the bottom here is all of the people that tested positive. So it's all of the people that tested positive that have the disease over all of the people that tested positive. Exactly what we were doing here. That's where the 45 over 140. 140 is all of the people that tested positive. 45 is all of the people that tested positive that had the disease. Well, the top part's clear. Sensitivity times prevalence is the percentage of people that have the disease that also tested positive. In other words, 5% of the population has the disease. We were right 90% of the time, so 5% times 0.045, 0.045 of the population is the ones that that tested positive and have the disease. They're on top. Well, here, the first part of this is the same value. people that have the disease that tested positive, right? Now, over here is people that tested negative that have the disease. In other words, the false negatives. How do we get that? Well, the specificity tells us how good we are at predicting people that don't have the disease. 1 minus p represents the percentage of people in the population that do not have the disease. Well, that would be, since the prevalence is 95 as 5%, 95% of 1 minus p, 95% of the population doesn't have the disease, right? So of that 95% of the population that doesn't have the disease, well, the specificity tells us how often we'll correctly get a negative from out of them. 90% of the time, we'll get a negative for those 90% of the people. But 10% of the time, 1 minus 0.9, that 0.1, that 10% of the time, we'll get a positive for this 90%, 95% of the population. That's why it's 1 minus the specificity times 1 minus the prevalence. This is the percentage of people in the population that don't have the disease that test positive. This is the percentage of the people in the population that do have the disease that test positive. And on top, the percentage of people in the population that do have the disease that test positive. So it's the percentage, it's the number of people that do, proportion of the people that correctly are identified as having the disease that's positive over all of the people, the entire proportion of the population that tested positive. That's our positive predictive value, same way we calculated it here. That's really what that formula boils down to. Okay, let's go back and move on. Okay, so we got diagnostic tests. Okay, variables. Quickly, let's go through. We could do a million of these if we wanted to. Typically, we're looking for categorical or nominal. It's basically the same thing. Whoops, put my pad down here so I can control the mouse. Ordinal, which is another version of categorical, but it's one that involves some order. In other words, the values have some order to them. One value is greater than the other, not just another category. Discrete, which is a numerical variable, which can be expected to be an integer, and continuous, which is a number that's on a continuous scale. That's a scalar number. Okay, so which one of these best? We always wind up with some one of these where we wind up having a debate on them. But let's talk about school type: primary, secondary, post-secondary. What kind of value? What kind of variable you guys think that might be? Opinion? Well, I think you could conceivably say that that's a categorical or nominal variable, right? But I think it might be a little bit. I think it might be a little bit more appropriate to call it a ordinal variable, right? Because post-secondary is higher than secondary is higher than primary. I think you could have a debate about whether that's categorical or ordinal. Okay, so we'll leave that debate for some other night. But I think you could probably get away with calling either one of those. I probably would have chosen ordinal. Mortality rate due to disease, number of deaths per 100,000, 20 per thousand, 20 per thousand, 23.7 per thousand. What kind of variable is that? Okay, continuous, I agree. Okay, ranking in an Olympic event, gold, silver, or bronze. That one's a little bit clearer to me, right? I think that's ordinal. That's definitely ordinal. We could have argued about maybe what kind of schools and so on and so forth. But that one I think is clearly, first place, second place, third place, right? So we don't know the difference between those, right? Let's say if we were talking about a race, we don't know if the difference between gold and silver was 1 second, and the difference between silver and bronze was 10 seconds. We don't know that. We just know gold is higher than silver, is higher than bronze. Occupation: nurse, teacher, candlestick maker, right? Categorical. Number of people in a study group. In other words, you get together at lunchtime and stuff like that as a study group. Number of people in the study group is going to be discrete. It's a numerical variable, but since it's going to be an integer, reasonably small integer, that we usually, like number of siblings or something like that, we'd say it's a discrete numerical variable. Okay, BMI. Excuse me, that wouldn't be in pounds. There's no, are there, I guess there are units for BMI. Body mass index. I guess there are units. I'm not sure what they would be, kilograms per square, whatever, inch, centimeter, or something like that. Okay, that would be continuous also, I agree. Okay, below is data from a randomized trial designed to evaluate the effectiveness of a newly developed blood pressure medication designed to reduce blood pressure in elderly patients. The trial compared the new blood pressure medication to the blood pressure drug currently in use, called the standard of care. The outcome of interest was the reduction of blood pressure rating. 3 or more scale points are considered to be a clinically meaningful reduction. So this is what we got here. We got the old medication and a new medication. We got the old medication. The new medication, okay, we got meaningful blood pressure reduction in 35 patients, and no meaningful reduction in 15 patients that took the new medication. The old medication, we got 30 patients that showed a meaningful reduction and 20 patients that showed no meaningful reduction. Okay, and you could also look at it from the perspective of the columns. Let's see, out of people that showed meaningful blood pressure reductions in this study, we got 35 on the new medication and 30 on the new. There's a number of ways you could look at this chart, right? Let's look at the questions. Let's interpret the questions now. What is the probability of experiencing clinically meaningful reduction in blood pressure given that the patient received the new blood pressure drug? Okay, expressions of the decimal case. What's the probability of expressing a clinically meaningful reduction in blood pressure given that the patient received a new blood pressure medication? So we're only given that, means that they all received the new, that the condition it's already satisfies, they got the new one. They didn't get the old one, they only got the new one. So what's the probability that they had a meaningful reduction? Right, 35 over 50, right? 50 patients got the new medication. Out of that, 35 got the had a meaningful reduction in blood pressure. That's kind of a conditional probability, right? Our starting condition was only people that got the new medication, and then we want to know what percentage of them had a meaningful reduction. What's the probability of experiencing no clinically meaningful reduction in blood pressure given that the patient received the old blood pressure medication? So now, given that they've received the old blood pressure medication, what's the probability that they experience no clinically meaningful reduction? Okay, well, in that case, how many patients got it? 50. So what do we think that is? 20 over 50, right? This satisfies that condition, 20 over 50. Good. All right. So you can see that we could, now you remember that table that we worked with, the divorced and single and male and female and so on and so forth. That had many more boxes, so we had a little bit more flexibility in terms of like asking questions that were relevant, that were kind of conditional probabilities. So you might see something simple like this, or you might see something a little more complicated like that. Okay, descriptive statistics. Well, I'm going to go back to my usual candidate here, NC Birth 800 mod. I have a copy of it here. I'm not sure I uploaded it to Blackboard. You have versions of it on Blackboard. I'm not sure if it's exactly the same version as this. But one of the things we might ask you to do is to find all of these various statistics. Okay, and also to produce some graphics. For instance, produce a histogram and a box plot. Well, what variable are we interested in analyzing this time? Number of variables in this data set. Okay, calculate the following statistic for the variable gained. That variable gained is actually the weight gained by the mother during pregnancy, not the baby's weight, but the mother's weight gain during pregnancy. Okay, so we want to look up all these various statistics for it, descriptive statistics, obviously. Okay, so I'm going to open that in SPSS. I'm going to open that file in SPSS. Now you can do this if you want. You can, well, presumably whatever data set we give you, we'll give you as a format as a CSV file if you're more comfortable with R and so on and so forth. And if it's a simple one, maybe we'll give you an Excel version of it or something like that. It might be a little bit, some of these bigger data sets going to be tough to work with in Excel, cumbersome to work with. not so much tough to work with. Let me get this out of the way. I need to get to my folder here. Where did I put it? Oh my goodness. I put the NC birth 800 mod. I want the one that's capitalized. I thought it was on my desktop. This is on my desktop. See if it opens up. Okay. Is it opening? Yeah, it's bouncing. Okay, see if we're successful in opening this. Okay, so now here's our database. It opened up in the data view. Okay, the one we're interested in is gained, weight gain, numerical variable. So it's appropriate for us to do these descriptive statistics. If it wasn't a numerical variable, let's say we wanted to check the gender of the infant that was born, right? We would use frequencies for a nominal or categorical variable. For instance, analyze descriptive statistics frequencies for the, let's see, that would be the sex of the child. Okay, and maybe if I wanted a chart, I might ask it to make a bar chart for me. Okay, and I'd say okay. And sure enough, SPSS will produce a bar chart. There's a few more female babies born than female babies in this particular. I guess that's true. And is that true in general? I think there's more female babies usually born nationwide than male babies. I'm not positive about that, but some you guys probably know that from an epidemiology class or something like that. You guys know? Are there more female babies born or male babies born in the United States in a given year? Anybody know? Well, that's what Google's for, right? So at any rate, this will give you the actual frequency. 418 males versus 382 females. You can see it graph up here. Notice the bars are separated, right? Because it's a categorical variable, right? It's not the continuous number scale here. It's just males, females, right? Number of babies, right? And the height represents the number of babies. Okay, so that's how we might handle frequencies. Now, for the data we were after for the weight gain, okay, I'm going to just click back here, analyze, descriptive statistics. Okay, so now you guys know that I go to descriptive statistics, I go into descriptives. It'll give me kind of a basic version. I can move the sex of the child in here. It'll give me a basic list of descriptive statistics. Right here it comes up. Gives me the mean. Okay. Now the mean really doesn't mean anything for this, does it? Right? I really should have gone back. We don't do means or standard deviations for categorical variables, right? We only do it for numerical variables. So instead, I'm going to go to Analyze, Descriptive Statistics, Descriptives, and instead of the sex of the child, I'm looking at the weight gained. Notice how you get a tip-off on the weight gained during pregnancy in pounds. You get a tip-off from SPSS. It shows it as a scale, a ruler, as opposed to these different colored balls and stuff like that. Okay, so I'm going to put the variable in there, click OK. This time it will give me a legitimate minimum, maximum. Somebody had no weight gain during pregnancy, seems unusual, right? 95 pounds during weight gain during pregnancy. That sounds like it's probably an error, right? Some data error. Okay, and there's the average weight gain. There's a standard deviation for the weight gain. It gave me a basic set of descriptive statistics. Didn't give me all of the ones that we asked for. If we were to use instead, again, we get same starting point. If you get stuck, just think, analyze. I want to do descriptive statistics. Frequencies is for nominal data. Descriptives is for numerical data, but it's only going to give me very abbreviated set of descriptive statistics. Explore is when I want to get more information. Click Explore, and again, I'm going to put in the numerical variable, right? The descriptive statistics we do is for numerical variables. The weight, let's see, weight gained, weight gained. during pregnancy. I'm going to move that in there, right? And I'm going to go ahead and do this. Now I'm going to click on statistics here and just look up. Descriptives is checked off. That's okay. I'm going to go into plots and make sure, since one of the parts of the question was to produce a histogram, I'm going to click histogram, so it will produce the histogram for me. Okay, it normally, when you use Explore, it always produces a bar chart for you. So a box plot for you. So we don't have to check that off. So I'm going to click OK, and it'll go ahead and calculate that for me. And here we go. All of the stuff that we asked for: mean, median, variance, standard deviation, minimum, maximum, interquartile range, so on and so forth. All of that was provided here. And here's our histogram for our weight gained. Here's the person who gained 95 pounds. That's skewing the results to the right or positively. That person's now that might be an outlier. There might be some reason that person gained 95 pounds. It also could be that it was a typo as the data was put in. So it'd be a good reason to go back and examine that. But it looks like it's skewed in general. The data is skewed to the right. Okay, so at any rate, so that would show, here's our mean is also displayed here as well. Now, we got our box plot here too. Here's our box plot, and notice that a lot of these higher weights are in an area that SPSS is suggesting might be outliers. Our median is going to be this black bar, not mean, but median is going to be this black bar, which is about 31 pounds or so. Our lowest value is this feather down here, which is 0. Our highest value was that 95. That 750 refers to the number, the subject number, the line in the SPSS file that that person is in. Okay, and actually, if we exclude all the outliers, it's picking out as our upper range, picking out about 70 pounds. The bottom part of this box is a 25th percentile. 25% of the women gained less than 22 pounds. 25% of 75th percentile is here. 25% of the women gained more than about 42 pounds. And 50%, the middle 50% of the women were between, looks like about 20 pounds and about 42 pounds. You can actually see that in the previous, you can actually see what those numbers actually are, right? 25th percentile. We have it here. Interquartile range is 20. No, it doesn't show the percentiles. Did we ask for the percentile? I'm not sure. I think we might have. Here we go. Let's see. No, it doesn't show it here. Percent minimum maximum. Interquartile range is 20. So that would probably be 10 on either side of the median, roughly. 5% range. Okay. So at any rate, that's what we would show for that. Now, the next part of this problem, okay, and I'm trying to remember, where did we see the interquartile range? Was there something I could have checked to give me that here? I remember seeing it in one of the outputs. Let's look into statistics. Percentiles. If we had checked percentiles, we would have gotten in our output, we would have gotten those various percentiles. Let's look at it this time. See, this time it gives us the 25th percentile and the 75th percentile, okay, for this distribution. Okay, so that little checkbox gives me that extra information that I need for if they had questioned me. Let's see, did we ask for it? Yeah, level 25th, we did ask for it, so you do need to check that box off. Does top line represents? Yeah, for the most part, yes. That represents 1.5 times. That's a kind of a default range that SPSS uses for values that it expects to be above the 75th percentile. So anything above 1.5 times the interquartile range, above the 75th percentile, it considers an outlier. Now, whether or not you should genuinely exclude that from your data is a judgment call. right? It may not be something you want to leave to SPSS to do automatically. So we're not concerned with that right now, but later on we're going to we're going to take a closer look at that. Okay, so let's go back to our Word document if I can find it again. Okay, look at the last part of this, which was, okay, descriptive statistics. This time, calculate the statistics for variable gain, the same variable that we were talking about now, except let's look at the weight gained by the mother factored by the gender of the infant. In other words, the mothers that have male babies gain more weight than mothers who have female babies, and also produce histograms and side-by-side box plots. Well, again, SPSS is going to help us out on that. And we're going to go through the same process. We're already have the file open. So I'm going to go to Analyze, Descriptive Statistics. Since we're looking for this expanded group of statistics, I'm going to click Explore. And weight gain during pregnancy is already in the dependence list. That's what we're going to analyze. Okay, but now we want to break it up into two groups based on not the age of the mother, not the based on the sex of the child. So now it'll separate out the data for weight gain during pregnancy for all of the women that had male babies versus all of the women that had female babies and analyze them separately, with the exception of the box plots, which it'll put on the same graph side by side. So I'm going to click statistics, and sure enough, descriptives is checked. Now, if you need the percentiles, you would check the percentiles also. Okay, plots, histograms is checked. Box plots are going to be produced automatically for us. And I'll click OK. And let's see if it produces. Okay, sure enough, here's our mean and various statistics for our for the male babies, 30.69 pounds. And for the female babies, women gained 30.5 pounds roughly. Well, there is a difference. As we go through the semesters, we're going to try and figure out, based on the variability, standard deviation here is 13, standard deviation here is almost the same, right? That's a very similar standard deviation. Based on the variability, we're going to determine whether or not this is a statistically significant difference, whether this difference is due to chance or whether the difference is really a difference in the average weight for all female infant births and all male infant births in terms of weight gain to the mother, or whether the difference is just due to chance. Now, would you say that this, even if there is a statistically significant difference, doesn't mean that the difference is clinically significant, right? Would you guys say that that's clinically significant, the difference between those two weights? I don't think so, right? The difference is so tiny that I don't think it makes much difference. That there really isn't a practical difference in weight gain for female versus male babies in this study, based on this study. Okay, so that's how we would do that. Here's our percentiles. If somebody asks us for the percentiles for the different groups, 25th, 75th interquartile range. And here's our histograms for each of the two groups. And here is our side-by-side box plots, which suggests, boy, it don't look like much difference between these two groups, does that? Right. So these this is for males, this is for females, and so on and so forth. Okay, so I think that